As mentioned, I'll be talking about building private applications, which are applications that allow users to take control of their data and make sure that their data is private using the Sunscreen FAG compiler, which is the compiler that I've been working on along with some coworkers and friends for the last few years. So when we're transacting online and we're doing any sort of, I guess, anything online where you're interacting with a server, we end up implicitly trusting third parties to keep our data safe. So what happens when we're actually interacting with a server? The most modern thing, which is quite nice over maybe what we had before, which was just everything was in the clear, was that we have some data from the user. We send it over to a server for some data processing. Now that process, when we send over the data, is encrypted, so we use HTTPS and certificates and these types of things in order to try to keep the data safe while it's in transit. But while it's on rest on either side, it could be unencrypted. The server will then process the data for us, do something useful for us. I mean, that's why we're sending them some data. And then likely they will send us a response back over another encrypted channel, TCP with HTTPS and that type of thing. But what's important to note in this diagram is that the data, once it's gotten to the server, is in the clear. There are certain cases where it might be encrypted at rest, but at some point when the server actually needs to process it, it needs to be just regular data, not encrypted data. So how do we use these types of things, or why do we need to know this type of data? So say, for example, you're doing online shopping, going through Amazon or something like that. The website's not exactly going to know what you intended to purchase if everything is encrypted. So it needs to be able to process your data in some form, and also needs to be able to process your payment information. Additionally, there are some other services, especially that have popped up more recently, such as like DNA services that need to know health data to determine relatives or genetic markers for certain diseases or other types of things. A lot of our healthcare has gone online as well, so you can log into online portals to access any of your patient data. All of that, of course, is stuff that you want to keep protected as much as possible. So the question is, can we really trust third parties with our data? And so under, I think the kind of nicest assumption is that we assume that all parties are acting as best as possible. But there are still a few cases where our data isn't necessarily as safe as we would like. So one case is data misuse, and basically handing off data to people who it shouldn't have been given to, or analyzing data in ways that it shouldn't have. Kind of common example of this one is the Cambridge Analytica scandal. So essentially data there was like, it was meant to be held, or it was held in this case by Meta or Facebook, and provided to a third party without necessarily the necessary checks that a user might want to ensure that their data wasn't used in ways that they didn't actually consent to. There's also malicious actors. There was a case for the Equifax had a large hack in 2017 that involved the breach of a lot of people's data. They actually set up another website to have people check whether or not their data was exposed during that breach. And then during that process, they actually set up they used a shared certificate with some other websites, meaning that it was somewhat easy to impersonate the Equifax website and potentially steal people's data. So that's the case of not necessarily like misusing data, but someone coming into the middle of the process and trying to take data for their own use. And of course, we have the kind of standard data breaches that we might all be too familiar with, unfortunately. So an example of this one would be 23andMe. 23andMe had exposed some data related to DNA relatives. This is highly personal information. And yeah, so essentially people they had trusted 23andMe to hold their data, and for a long time they did hold that data properly. But at some point, they unfortunately had a data breach. It's, as much as we try in security to provide as many safeguards against exposing data and stuff like that, we unfortunately can't handle every case. It just takes one faulty brick in a wall for the whole wall to come crumbling down. So the kind of takeaway from all this is that even if we do trust a third party with our data to do the right thing, our data isn't still necessarily safe. In the case of some companies like 23andMe and ideally Equifax, they're trying to hold your data in confidence and unfortunately succumb to attackers. So the question is, can users keep their data private while still using all their favorite online applications? And my answer to this is yes, and we can do so using a technology called fully homomorphic encryption. So what is fully homomorphic encryption? So it's kind of broken up into two pieces. We're going to focus on just the homomorphic encryption part first. So homomorphic encryption allows data to be processed while remaining encrypted. It actually never gets decrypted like in our prior examples. So maybe for a basic example, if you want to add two integers, there's kind of two ways you can do it. The standard way is on the right side of this equation, which says that you could take A and B and you can add them together, and then you can encrypt the result. So the plus D stands for the fact that you're doing it on decrypted data or just plain text data. Or there happens to be another way where you can basically encrypt A, encrypt B, and then add them together and get the same result as if you had performed the computation on just A plus B and encrypted the result. So maybe this is helpful to see as a diagram. So essentially there's kind of two paths you can take in this diagram. Either you can take the top path, you can go A plus B, calculate that and get A plus B, and then encrypt it to get the encrypted answer to send to someone. Or you can encrypt A, you can encrypt B, and then you can add those and get the result. You won't get precisely the same ciphertext, you'll get the same data, but each ciphertext or each piece of encrypted data will have its own randomness and will encode the same information. So the fully part of the fully homomorphic encryption means that any computation can be performed on encrypted data. So this does come with some caveats. So essentially it means that in some senses it's something similar to Turing complete. You can calculate anything that you'd want to. However, some things are very difficult to calculate in such a system. And so there might be things where it's like, well, potentially I want to calculate something. Maybe I want to do a physics simulation in encrypted data. There's a slowdown related to processing encrypted data, and there's also a blow up in data size. Probably not the right application. You could do it, but it's probably should focus on things that are a little bit more reasonable to the system. So let's review again kind of like what we're talking about here. In the traditional application, we send data to a server encrypted, and then the server will then process that data unencrypted and produce some sort of result, and then it will encrypt that data and send it back to us. In this new paradigm, what we do is the user will encrypt their data locally with their own key, producing an encrypted result. They will then send that data to a server who will then process it without ever decrypting that data. So at no point does the server actually know what was contained inside that encrypted data. To all they know, they were literally given random byte strings. They will produce some sort of result. That result will be sent back to the user, and then the user can decrypt that data as they see fit. Well, they probably want to. They probably just don't want to hold on to it, and get the result of that computation. So what's the challenge with current FHE setups? Why are they difficult to use? Well, currently when you're using an FHE setup, the developer or the user really needs to know cryptography quite well in order to choose the right system and parameters. The system we happen to use primarily at the moment is called BFV. There's another one that we're working on called TFHE, which is based on torus elements. And there's other kinds of things where you have to know polynomial arithmetic and other types of things like that. So it gets quite complicated. Making a computation performant is quite difficult, even for experts. There's a lot of parameters involved in trying to tune these systems such that you kind of have a trade-off of security and speed and data size and these types of things. Finding the optimal tuning parameters inside there can take quite a bit of time. You can get incorrect results while performing a computation if it's not quite performed properly. So essentially, any encrypted data, one of the kind of tenets of encryption is that there's always some sort of randomness. In the case of schemes that we're using, there's a bit of noise that's added to the message to obfuscate it. So that noise that's added grows as you perform more operations on the encrypted data. And there might be a certain point where you perform too many operations on encrypted data to be able to correctly decrypt it. You will be able to decrypt it, but it will just give you some random number instead of the result that you want. And then it's also hard to translate some problems into FHE primitives. So the main primitives for the BFD scheme that we use is addition and multiplication. Turns out you can express any computation using those primitives. Some more difficult than others, but it's hard to necessarily take your program that you would just write in Rust and then turn it into an FHE program by trying to figure out exactly how those map to arithmetic circuits. So that's where we come in with the Sunscreen FHE compiler. So the Sunscreen FHE compiler makes it easy to convert standard Rust into encrypted forms that work on encrypted data. So here we have our add example that we were talking about before, just in the working on plain text data, on clear text data. So you just take an A that's a signed value, a B that's a signed value, and you return another signed value, and then it's just the addition of them. Now the only changes that you need to make in order to turn this into an encrypted version is essentially a macro on top and some types. So essentially you add this attribute on top, you say FHE program. Currently this scheme that's supported is BFV. We're adding support for other schemes as well. And then you'll notice here that the type changes. So the type before was just I64 signed, is the equivalent of I64, and then the wrapper cipher essentially means that it's encrypted. So how do we run this program? It's not quite as simple as running just a regular Rust program where you would just call add with whatever values. You need to encrypt the data first, since we're working with encrypted data. So the way this works is that you call the compiler, you make a new instance of it, and then you add in the program that you want to compile. This will generate an application that has some parameters. So it basically runs your program to try to figure out what are the optimal parameters in order to make your computation fast and perform it yet still secure. You then pass these parameters to a runtime and then get out the FHE program that you want to run. You can then, with that runtime, generate the keys in order to generate encrypted data. So this is kind of like SSH or any sort of asymmetric key system where the public key is used for encrypting and the private key is used for decrypting. In this case, we'll be encrypting just the numbers 15 and 5. And then finally, we'll run the program using our runtime. So here we just pass it the program that we want to run, add, and then we pass in the values. So add with A and B, also passing in the public key. This will produce an encrypted result, so that result has type of essentially cipher of signed. And then we can decrypt that result using our private key. So at this point, you could consider all of this was done on a local machine, but one thing that's kind of nice about all of this is that most of these types are serializable. So you can take the ciphertext, the plain text data, the encrypted data or the plain text data. You can take the programs themselves and also the parameters and send them over to a server to be run. So what types of data do we support with Sunscreen? So we have a few basic types. One of them is equivalent to a unsigned U64. We also have different bit widths of that one. So we have unsigned 256 and those types of things. These ones support, under the BFB scheme, essentially plus, minus, and multiply. And then you can also operate on both plain text and encrypted inputs. We also have a signed variant that essentially is the equivalent of an I64 and has the same properties as unsigned, but also has the ability to do negation. So if you had 5, you could have now -5, but encrypted. We also have fractional values. You can somewhat think of these as floating point. They're more akin to fixed point. Essentially, that n value there is how many bits you want for the integer part. And the rest of the decimal part is actually related to the parameters chosen by the scheme. Oftentimes, you have many more decimal parameters than you would in a standard floating point. So if you have dimension 1024, if you're using only 64 bits for the integer part, all of the rest of them are for the decimal part. So the advantage of this is that you can do kind of more like arithmetic on closer to real numbers. And you can also divide, in this case, by a constant value. Not by an encrypted value, but by a constant floating point value. And then we also have a rational type. So the rational, you can somewhat think of as a signed over signed type. And this one actually has all the properties that you could think of before, except for as signed, except for you can divide by an encrypted value. One thing to note is that the first 3 are more performant than the last one. So the last one, because you essentially are doubling the amount of ciphertext you're dealing with, you have now 2 assigned value over assigned value. You're now dealing with something where it takes more time to compute things, the noise grows faster, so you'll have to put in more refresh operations. The other part that you've seen here so far with in relation to types is that cipher wrapper. So if you see cipher of T, that denotes that you have an encrypted value in either an argument or a return type. The absence of this wrapper just says that you have the unencrypted type. So that one's somewhat easier. You can just say like 7.into to get like a unsigned or signed variant of that one. Cipher is unique in the sense that it's not possible to just do if you're familiar with Rust, there's no like from trait or into trait. You can't just generate one. You have to use the encrypt and decrypt functions in order to generate a cipher value. So talk a little bit about like how you can basically test in different types of cases. So here you can test a function that's both generic and the encrypted variant. So here we have add, but we've made it generic over a type T, where we've said that the type T essentially has to implement the add function. And then if we want to use it in an encrypted form, what we do is that we just now call that function with the parameters that we were interested in, with the types we were interested in. So what's the value of this? We're able to test functions in both an unencrypted sense and an encrypted context. And this enables FHE programs over many more types. So One thing that needs to be known by the FHE compiler is that it needs to know exactly what types you're dealing with when it tries to compile the program. You might not want to write this encrypted add for absolutely every single types you might have as an input. Like you could have cipher signed and then signed as B, or you could have signed and cipher signed. You don't want to write all those variants. What you can do is write the generic type or generic function up top, and then call it with the types that you care about. We can also accept mixed inputs. So for example, what you could do is, and these operations are cheaper than the encrypted variants, but essentially both sides of an equation don't necessarily have to be encrypted. So here we're taking A and B, but in this case B is not encrypted, it's just a plain text value. So we're taking an encrypted value and then adding in a plain text value. We also support operations over arrays. So here is an example of an array using the generics that we had talked about prior, where we have an array of some size n. And then one thing to note here is that when we're dealing with this one is that we don't have a definition of 0, so we actually pull out the first element and call that and iterate over that, use it as our place to store all of our data. So we first pull out the 0 element, and then we add to that each successive data element in the array. Then if we want to call this in the encrypted form, we just call our generic function that we have with the types that we care about. Now note that for this to work, because the compiler essentially needs to know how many operations you're performing in order to generate the correct parameters, what it will do is you need to have that 10, some sort of constant generic or constant number there that it knows about, so it can actually compile your program correctly. So what's important to note here is you can operate on arrays, but you cannot operate on dynamically sized objects such as vectors. Now what you can do is you can write a program that expects a certain size, collect data with a vector outside of the FHE program, and then try something like try into in order to try to convert it into an array, and then use that array inside your FHE program. Then the failure will happen before you do the FHE computation itself. There are some restrictions. So there's no comparisons in the BFE scheme. We are working on a scheme that does allow for comparisons, but essentially you can't say, here is what is somewhat equivalent to a MUX circuit, if you're familiar with hardware. So essentially you would take a select bit and you want to say if it's 1, then you select A, if it's 0, then you select B. This will not work because you need to basically, you cannot do that comparison there, that if select equals 1 component. However, comparisons are okay if you do it on constant data that is not actually passed into the function. So here we have data that says, we have the for loop that generates an index, and then we have an if on the index of that for loop. That is okay because none of that data is actually coming in from the input arguments themselves. We also can't similarly operate on something where we don't know the size of it before runtime. So here we have a for loop, and the problem is that we're essentially going from 0 to B, whatever the size of B is, or whatever that value is. But since we don't know what that value is when we try to compile the program, we can't actually run this one. So the Sunscreen compiler will tell us this and make it impossible to actually run. What you can do, similar to the other one, is that if you have constant expressions, here you happen to know that you're doing 5 iterations, then you can run a for loop. There's some other operations that probably are a little bit, the Sunscreen compiler will detect for you, and you generally want to avoid them anyway, so it's good that we find them. So essentially there's cases where you can do operations on encrypted data that probably will break the security of your system. So one of them is if you take a ciphertext, if you take some encrypted data and subtract it from itself, they'll necessarily always be 0. So we generally don't want to do that. That leaks information about kind of what's going on in the system. What you can do is that if you had instead that subtraction where you took in a B type as well, or a B value of cipher signed, you could subtract those if they were encrypted independently. So encrypted under the same key, 2 pieces of encrypted data, they both look completely random, those you can subtract. The data inside will be 0, the underlying message, but that will be an allowed operation. Similarly, if you multiply by a just plain text 0, that's also a bad case. That will just lead to encrypted data that's all 0. All of the message and randomness is gone. And similarly to the prior case, if you supply an encrypted 0, then it is okay. Because then you're taking an encrypted data, which again looks kind of like random numbers, and you multiply random numbers by random numbers and get out what looks random. There's also bounds on the computation. So essentially, I had mentioned that the ciphertext has a bit of noise in it along with your message. Every time you process that data, the noise grows within it. So there's a limit to how much you can do before you can no longer decrypt the data. Here in this case, the Sunscreen compiler will also tell you that it was unable to find any parameters that will basically satisfy this. I've done too many operations in order to correctly perform this repeated multiply. So let's look at some examples of FHE programs. We're going to go through 3 basic examples. One, we're going to calculate the statistics on top of encrypted values. For the next set of examples, I'll show you through some websites that we have, some private ML inference on a few different cases. And the final case will be how to perform private auctions. So for the statistics on encrypted data, so say a service wants to provide some statistics for a client. In this case, we're going to focus on mean and variance, but they don't necessarily want to share, the user doesn't want to share their data with the server, and potentially the server doesn't want to provide the information required to process the data. So maybe they have a proprietary model for how they understand the data that they have, or the data that they are receiving. So in this case, we'll go through the code a little bit. It should look pretty familiar to the sum case. So this is the equivalent to the sum case where we have a generic function where we're taking out the first value and then we're adding into that value as a temporary storage. The difference here is that now we also have an additional constraint by this divide by F64. So now we're saying not only do we need types that support add, we also need types that support division by floating points. And then you can see here that we actually do perform that. So when you're doing the mean, it's the sum of all the values divided by the number of values. So we are able to do this if we use either a fractional or a rational type. Now for the variance is calculation of the variance is essentially you take the mean of the data, you subtract each data element from that mean, square it, and then divide by the number of elements. Here you can see that we're doing that. So we have a few more constraints related to the fact that we're now going to do some subtraction and multiplication. And later on we'll use the mean, so we'll need the division part. So essentially we calculate the mean, we clone the variance in order to get each data value again, and then the for loop essentially just does that mean subtraction and then does the squaring without using the POW function. It just does it by the temporary value times itself. And then we run that mean function on the variance that we pass in. Now note what's kind of cool here is that we can reuse the FHE functions that we had before. So this allows us to compose FHE programs and kind of build up a library without having to manually or silo each of our programs away from each other. And then to run the data is kind of as you would expect. The server can run the encrypted data by essentially specializing this generic functions we have for the types that we care about. And so this allows for a few different things, as mentioned before. The user gets to keep their data private, and the server also gets to keep its statistics model private. So if it has any private weights, it might have some plain text data related to, I have some sort of model, and I have plain text data related to the weight I've assigned to certain variables. This will allow the server to keep those private. We also have private machine learning as an example. So we can do FHE-based ML inference that allows users to keep their data private and to keep the ML model also staying on the server. So the user doesn't necessarily need to download that ML model. So let's see. For this example, we have a few different cases. Here, we're having this is a demo that runs on a server in AWS. And essentially what it does is it asks whether or not a transaction is fraudulent based on some information. So here, I'm going to start predicting this, but essentially the parameters that go in are a distance from home, purchase price, the distance from the last transaction, and the median price, along with some information as to whether or not the chip was used, or the card was used itself. So this data is encrypted and then sent up to a server, processed, and then returned. This particular case is a 3-layer neural network. So essentially the user is able to send up their data, get information such as this transaction looks legitimate, and then receive the result and only private to them. So the server actually never learns anything about whether or not that transaction, they don't know anything actually about the transaction. They don't know what the purchase price was, they don't know what the distance from home was, they don't know anything. They just know that they received some sort of data related to transaction, that they threw it through their model, and that they gave it back to the user to then decrypt the result. So here, we're running another example. where the distance from home is significantly higher, and it's an online purchase. So here, the model that was detected detects fraud. Then as a kind of another example, here, this is a different case where we're trying to detect whether or not you have a high risk of a heart attack. So in this case, we're not using a neural network, but logistic regression. So here, if we fill out the form with kind of the information that would predict a high case of heart attack, we can send that to the server, and then you can see here that it says you have a high risk of a heart attack. So this information could be sent, say, to some sort of, maybe a user wants to know about this without necessarily providing their health provider or someone else with information about their current health status. They want to know some information, but they don't want to reveal it. And then similarly, the server doesn't have to reveal how it actually calculated this component. And then finally, the last example we'll go through are blind auctions. So blind auctions are where all bids are private. You don't actually know, unlike a normal auction, maybe where you're sitting there and you're trying to figure out, hey, like someone else bid $5, now I'm going to bid $6, and I know the history of this particular person always bids in this particular behavior, and trying to come up with a strategy here. You can't actually do that. All bids are private, and what happens is that only the winner is determined and reveals their bid and is able to purchase whatever the item is. So there's some benefits to this model. Sometimes you also hear it as it's similar to something called a Dutch auction. So you don't reveal the strategy that you're using in order to bid on something should you lose. So if you win, you do reveal something about a small amount of information related to the maximum price you're willing to pay for something, or what you believe is a reasonable price. But if you lose, you don't necessarily reveal any of your bidding history. Additionally, it often leads to more genuine bidding because they don't know the context of others bidding on the item, they'll bid what they think is the fair market price for it. So the question is, can we do this without necessarily trusting a third party? If we were to provide all these bids to a third party, one of the challenges might be is that they could potentially put in their own bid that supersedes any of ours. Or maybe we just don't trust them in general to run the computation. So here is an example of doing that. So here we have, and this is online on our blog. So you can basically see that there's 92 other people who are bidding, virtually in this case from a server, or they're simulated, and then we can put in a bid ourselves. So the bids in this case must be between 5 million and 7 million. So we can participate in the auction by sending up our bid. It'll all be executed, and then we'll find out whether or not we won. In this case, we didn't. And for specifically just the fact that this is a demo, we can see what they actually bid as a value. So in this case, it was 6,997,000. However, if we provide the maximum, we're highly likely to win this auction. And then you can see here that it says that you are the winning bid. So in this case, this is using what I've talked about before. We have the BFV scheme. This is based on work on the TFHE, so this does allow for comparisons. But here you can see other applications where we're providing people with an ability to participate in auctions privately and keeping their data secure. So with that, that's the introduction I have to the Sunscreen FHE compiler. The Sunscreen FHE compiler makes it easy to make privacy-preserving applications. It reduces the risk of malicious data use because the data is encrypted and even the server doesn't know what's inside of it. It reduces the effects of data leaks, and also it gives users control of their data privacy. Now they are in control of the keys, and they pass off the data to the server, and they know that the server can't do anything with it. They don't know any information about it, and only they can decrypt the results. So with that, you can ask me some questions. There's also these QR codes that will provide you some information on. We have a Rust playground, which is similar to the standard Rust playground, but has our specific Sunscreen compiler, and the documentation we have for the compiler itself. Sure. Currently, we don't support strings. You could try to essentially encode strings using like say for example, you could use unsigned integers and use an ASCII encoding. The question is, what is like, our compiler mostly supports addition and multiplication, so what does it mean to add two strings? That one's a little bit more difficult. So we don't currently have support for string-based values. Yeah, so we are working on comparisons. So as I had mentioned, that we have the TFHE, which is the Torus FHE-based scheme. So we are working on implementing that. We don't have a ton of details at the moment, but that'll be coming out soon. As you can see, the blind auction was an example of using TFHE. So we are well on our way to actually like providing support with that within the Sunscreen compiler. That case will be also like kind of like everything else in cryptography. There's a little bit of a trade-off. So if you want fast comparisons, TFHE will probably be the thing you want to try. If you want fast arithmetic and doing like data processing and ML stuff, BFV will probably be the scheme that you choose. Yes.
So does this require that like the data be sent in an array where each individual integer in the array is encrypted separately, or can you just send the array encrypted all at once? And then I guess just kind of as a follow-up to that, like, is there a problem where if the typical data that gets sent tends to be small numbers, that people can just brute force it because they know that there's only a limited number of possible values that could have been sent?
Yeah, so as to your first question, so the way our compiler works is that when you encrypt an array, you can send over the whole thing at once. As for whether or not small values are a problem, so one thing that's kind of nice about these schemes is that when they're encoded, so the plain text data is like quite a small modulus, so you might have like data between say 2 and 1,000 or something, or 0 and 1,000. However, the actual space of ciphertext data, of encrypted data, is very large, oftentimes like the product of 4 primes, 4 unsigned large primes. So at that point, you're dealing with data that's like randomly distributed over a much larger ciphertext space. So even if you collected a bunch of data, it wouldn't necessarily give you an option to reverse that. So if you're interested in kind of some more details on these things, there's 2 topics called chosen plaintext and chosen ciphertext attacks, and then those will give you more information on kind of like what FHE is, like where FHE falls in those security parameters. Yes.
Is there anything you need to Rust that enables Sunscreen, or could you theoretically do the same approach in any language that has sufficient like operator overloading or generics?
Yeah, so you can certainly do it in any language. The mathematics, of course, is agnostic to the programming language in question. The reason why we chose Rust is because performance is a key challenge for FHE, and specifically also data management, because the ciphertext can be, so say you encrypt 1 bit, it could be 1,000 times larger, just encrypt that 1 bit than the 1 bit itself. So you don't necessarily want to, you want to use the move semantics of Rust to like move values around and not copy them as much as possible, which is a little bit harder in some other languages. Having said that, one thing that we also have supported in the past is that we have cases where we provided wrappers for Python and in Solidity in one case for the Ethereum blockchain. So you're able to perform encrypted operations in those languages by calling Rust on the back end. Yes?
I guess at this point, if you have more questions, I invite you to go up to the Q&A island up on the 4th floor for the water room. I think we're 3 or 2. So, well, you can figure out. So, yeah, but thank you very much, everybody, for joining Ryan's talk, and thanks.
Yeah, thank you for attending.
Thank you.